A huge thanks to Brian for sponsoring this video. Good morning, fellow mathematicians, welcome back to another video. Very highly requested after the last video on abstract algebra, we are going to continue with a simple and humble game of rock, papers and scissors. If you haven't watched the last video, make sure to do so. You can find it in the info box up here or down there in the description. So what we did last time is we talked about magma as, not magma, let me get to that. Rock, paper, scissors as an algebraic structure. We defined ourselves a set G with the elements rock, papers and scissors, and we have defined ourselves a beating relationship, a binary operation, where if we let A with B fight, we get out the winning symbol. And we found out that this right here forms together with the binary operation an idempotent abelian, so commutative, and also alternative magma, which was very interesting in and of itself. But I also told you at the very end that there is a cyclic nature hiding behind this rock, paper, scissors game. And this is what we want to talk about today. And it's going to be a very beautiful relationship between automorphisms, bijections and the like, and this rock, paper, scissors game, and the cyclic nature of just groups in general. So I hope you are going to enjoy the video. Stay tuned for the entire video. Please stay here. It's going to be very interesting and you are going to learn a lot of new stuff if you haven't heard about group theory before. By the way, this video has been sponsored by the wonderful people over in Print. More information at the end of the video. And now we are going to dive right in. So we are already done with the refresher from last week. Now, what we want to do is we want to take a look at this beating relationship, so what we have here with the winning symbol, in a little directed graph. What do I mean by that? I'm going to take our symbols that we have for a classic game of rock, paper, scissors, so R, P and S, and I'm just going to put those into a triangle order. And now we are going to connect those via arrows. It's pretty simple. And those arrows are always going to point to the winning symbol. Remember, we defined ourselves the operation as being fight, and then we are going to get the winning symbol out. Now, paper beats rock. So rock is going to point to paper. Paper is going to be beaten by scissors. So it's going to point to scissors. And vice versa, we have rock beating up scissors. This right here is our directed graph. This is also a little bridge to graph theory, just a very tiny little bit, not much. Now, what can you say about a graph like this? What does this tell us? Well, we want to get away from our regular relationship that we have embedded on our set G to this arrow right here. We want to turn this arrow into some kind of function, you could say, a so-called mapping. Now we are going to give this arrow right here a new name. I'm going to call it sigma because I'm a sigma male, obviously. Now every time we apply sigma to a symbol, it's going to do the same as what our arrow is going to do. Namely, it's going to spit out the winning symbol. Now, what does that mean in general? This right here is like a function. It's a mapping. We are going to take sigma and we are going to apply it to R, for example. What are we going to get out? Sigma represents our arrow in this directed graph. We are going to get P out, paper, because paper is going to win against rock. Now we also have the other relationships. If we apply sigma to paper, we are going to get scissors out. And the last one, sigma of scissors, is going to be rock. Now this right here are our three operations that we can basically do, because our set G only has three symbols elements in there. Now this becomes a lot more interesting if we take a look at our sigma that we have right here, our arrow, and we are going to combine it with our operation that we have embedded on our set G. Let me enhance the view a little bit for you. What do I mean by that? What we are going to do is we are going to create ourselves a so-called homomorphism. What is a homomorphism? A homomorphism is, in algebra, how can you describe it? It's something that just preserves the structure of an original operation. We have our binary operation, which spits out our winning symbol. Now what were to happen if we do, for example, sigma of, and now what we are going to do is we are going to take a look at our original operation A versus B, you could say. Now that's quite an interesting question, right? What is going to happen here? What we want to show is, if we want to see if this right here is a so-called homomorphism, something that preserves the structure, is if we get out sigma of A with the operation from our original group or magma or whatsoever with sigma of B. This right here, if we can prove that this is true for all the elements in our set G, then this right here is called a homomorphism. Just let it sink in. What are we trying to say? If A beats B, then sigma of A is going to beat sigma of B. That just means that our structure of the original operation is going to be preserved under this new mapping, this applying of the arrow right here. Now, that is actually quite easy to prove with our set. It can be quite hard actually, but the cool thing is, remember that our original magma is abelian, meaning it really doesn't matter if we take a look at A beating B or B beating A, so vice versa, it both holds. Now, what we can do is we can just go through all the combinations that we can think of, without loss of generality. Since it's abelian, we can just turn it around. And if we can show that this is true for all of those, then this right here, this sigma, is going to be defined as a so-called homomorphism, a structure-preserving operation. Okay, let us just do this real quick. We are going to prove that this is true. Let's take a look at sigma of. At first, we are going to take a rock against paper. Now, let's remember, rock against paper. In our original operation, what is this exactly? If we let rock fight against paper, paper is going to win. Okay, so this is going to be sigma of paper, because we are just computing what's inside of here. Okay, so we now need to show that sigma of paper is the same as sigma of A in operation with sigma of B, where A and B are R and P respectively. So let us put just an equal sign here. We can compute sigma of P. Sigma of P is gonna turn out to be scissors. So this right here is the part that's of interest right now. No, we are going to take sigma of rock and we are going to put it into operation with sigma of paper. Now, sigma of rock, we have this up here, is the same as paper. In operation with sigma of paper, this is going to turn out to be scissors. And would you look at that? Papers versus scissors? Well, scissors is going to win. This right here is going to hold. So we have checked for the first case. Now let us go through the other ones. If we have sigma of rock versus scissors, we are going to get sigma of rock versus scissors. Rock is going to win. Sigma of rock, we just talked about this, is paper. Now, on the other side, what we are going to get sigma of rock versus sigma of scissors. Sigma of scissors, we are going to get rock out. And sigma of rock, we are going to get, once again, paper out. If we have paper versus rock, paper is going to win. That holds. And now you can quite probably guess, if we have sigma of paper versus scissors, this is sigma of scissors, and sigma of scissors is gonna be a rock. Now, what are we going to get out? Sigma of paper versus sigma of scissors. Sigma of scissors is rock, and sigma of paper is gonna be scissors, meaning rock is going to win. And hence we can put our first QE motherfucking D down here in the corner. We have shown that this right here is indeed a homomorphism on our original set G. Now, to make it more clear, what does that mean? What are we doing with our operation sigma, our arrow? That is just a mapping which takes an element of G and puts it on G once again, where we have defined that sigma is just this triangle right here, basically. Okay, now a homomorphism in and of itself isn't that useful right now, so we have preserved the structure. So what is going to happen at first is going to happen here in this triangle too, but it's going to become a lot more useful and interesting If we take a look at the notion of an automorphism. So what is an automorphism? It's a homomorphism, which is also a bijection. Now, this escalates quite quickly. What is a bijection? A bijection is when you can inverse a function once again. So if you can take the inverse of a function, that means it's a bijection. It's on the one hand surjective and on the other hand it's injective. We want to turn this into an automorphism because it has a lot of cool properties that we can use, especially when it comes to the cyclic nature of the rock, paper, scissors game. Now, let's go ahead and get started. We want to show that this is a bijection. For this, you can take two paths. You can go the very, very fundamental route and show that it's a surjection at first. What is a surjection? A surjection just means that for all B out of G, there does exist an A out of G such that sigma of A is equal to B. That's all that it really means. This right here is just a regular line test that you are going to do in your calculus class, where sigma, as we mentioned before, is the mapping from G to G, and A and B are elements of G, our original set. And this right here is trivially true. We have proven already that this right here is a surjection because we know where all of the elements map to on our map sigma. Okay, that was easy. Now, so this right here is already done. It's a surjection because it's trivial. Now, the other thing is the injection. What is an injection? An injection just means that for all A and B out of G, it does hold that if we have sigma of A and we compare it to sigma of B, then this does imply that A is equal to B. So an injection just means that we can basically compare our arguments, and this ensures kind of a uniqueness, you can say. Now, this right here, I tried it. It's kind of hard to prove if you do it that way, but you can also go using the route of the contrapositive. Contrapositive just means that for all A and B out of G, it does hold that A is not equal to B, implies that sigma of A is also not equal to sigma of B. I think all of you can see that this right here is also a true statement. So if we can compare it here, then we can also say if those don't match up, then obviously sigma of A doesn't match up with sigma of B. And the contrapositive in this case, I haven't used this much during my studies actually on the injection, but here it does work wonders actually. And we can just go through this in the same fashion by checking for all the pairs. So if we say, for example, rock is not equal to scissors, obviously in our set G, then this does apply that, okay, let us check sigma of rocks. Sigma of rock is the same as paper. And this is obviously not the same as sigma of S, where sigma of S is rock. This is trivially not true. So for this part, it's injective. So we just need to check for the other ones. So if scissors is not equal to paper and paper not equal to rock, then this does imply in both cases that sigma of scissors is equal to rock. And this is not equal to sigma of paper, where paper is equal to scissors. This also doesn't match up. And if we have sigma of paper, this is equal to scissors. And this is obviously not equal to sigma of rock, which is paper. And hence we have another QE friggin' D. So just a tiny little recap. What have we done? We have turned our game of rock, paper and scissors into a directed graph where our arrows are represented by a mapping which just takes an element of G, our original set, to an element of G. We have shown that our structure, so whom again wins against whom, is preserved. Doesn't matter if we take our original game of rock, paper and scissors or if we take this directed graph. Doesn't matter, our original operation is going to be preserved. And also, our operation is a bijection, meaning next to our original function sigma, the inverse of sigma does also exist. And what the inverse of sigma is, we are going to talk about this in a second. It's an automorphism now, and this is very good. Oh, well, didn't see you there. Before we continue with the algebra journey, have you ever wondered if you could learn something like this online in a pretty new and exciting fashion? Then I have good news for you, because Brilliant are the sponsors of today's video. With their nearly 70 interactive courses in all topics STEM, it really doesn't matter if you want to learn something about abstract algebra today, physics, computer sciences, chemistry, they got you covered. They have so much content available on their website that you're going to be settled for a lifetime's worth of knowledge. No, on a serious note though, if you want to learn something new on the go or at home on a daily basis, then they could be the perfect fit for you. They provide you with some of the best online learning content that you can find out there on the internet, and especially for hard topics like abstract algebra and understanding symmetries and groups and the like. They are just the perfect resource online, which give you a good mix of abstract learning and also visualizations that you really don't find anywhere else. Just take a look at any of those things that I'm showing you right now here on the screen. It does look fantastic, right? Those are just smooth animations and things you can play around with. Their unique course concept is just learning by doing. You grab a lever here and there, take a function and transform it using knobs. Just play around with those things and see where it's going to get you. It's very playful, it's extremely interactive and a lot of fun to go through their courses. And as mentioned before, they cover so much stuff. Really doesn't matter what you want to learn today, they probably have it in store somewhere over on their website or app. So you have to just try it out and see if Brilliant could benefit you in any kind of way. Just try it out for completely free by using my link here down there at the top of the description. Try the whole landscape. Just see if Brilliant is something that could benefit you in any kind of way. And if it does, why not try to consider a long-term relationship between you and their services by using my link entirely and get 20% of an annual premium subscription using brilliant.org/flammy. Try it out and see if it's something for you. It doesn't hurt, it's completely free at first, so see if you could benefit from it in any kind of way and if you can master abstract algebra with it. Yeah, I'm going to erase the rest of my blackboard now and I'm going to see you in the next part. As mentioned before, doing the injection and surjection part is very fundamental. We could have done something different. We could have shown that sigma is invertible in and of itself. But what does it mean for it to be invertible? Invertible just means that if we take sigma and we put it in composition with its inverse, we are going to get the identity out. Now there are two terms in here that I have used. We have the inverse and we also have the identity. And this is where the really interesting part comes in. Now I can finally say it. Now what is sigma exactly? Sigma is, as mentioned before, an automorphism. That just means that it's an algebra preserving operation. It's just a renaming of our original operation that really doesn't change the algebra in and of itself. It's just a restructuring of the original thing. And this is where it's really interesting. Look at that. What is this exactly? Geometrically speaking, this right here is just an equilateral triangle. Now what is going to happen if you rotate an equilateral triangle by 120 degrees? Well, you might have guessed. It looks the same. And this is oddly familiar to sigma. Sigma just takes a thing and puts it to the next corner, you could say. We just show what is going to happen once we move it down here. It's like a rotation of an equilateral triangle by 120 degrees. And that's a very interesting thing. Abstract algebra, group theory, is so much about symmetries. It's just understanding symmetries in and of itself. And this is where the identity comes in. Now, what is the identity? The identity is just the thing that preserves the original thing. Meaning, how can we get back to our original corner here? By doing an operation. There are many things you could do, but the easiest thing you could do is just turn this by 120, 240, 360 degrees. So the identity is just an entire rotation. How can you achieve an entire rotation? Well, you can just use sigma 3 times overall. If we take a look at rocks versus paper, paper is going to win, then scissors is going to win, and at the end, rocks is going to win. Okay, that is very cool. So we can define ourselves an identity, where the identity function is just sigma applied to sigma of an element, doesn't matter which one in here. So this is just sigma cubed. This right here is our identity. So in order for us to get ourselves an inverse of sigma, we need to take it into composition with something else to get ourselves back to the identity. Now, what can we combine sigma with? I'm going to just use this symbol or any upper operation, really doesn't matter, to get ourselves the identity. Well, sigma is just a single rotation, so we need to do 2 more rotations to get back to the original spot. So this is just sigma squared, where sigma squared is our inverse. This is sigma to the -1, you could say. And there we have it. This right here is our inverse function. And it does exist. It's uniquely defined. So we can also see that this right here is a bijection because an inverse does exist for sigma. So that would be an easier proof, you could say, to show that this right here makes it a complete automorphism. But now we have gathered all the very important parts. We have talked about the symmetries in here and the rotations. And we also found out 2 operations, namely the identity and the inverse, which is sigma squared, which, if you think about it, preserve our original structure too. If sigma as a single rotation is going to preserve our original algebraic structure, then sigma squared is going to do so too, because it's just sigma applied to itself. You can get back to your original position by taking sigma squared 3 times. This is 240 degrees, then we get 480, and then 720 degrees. This is the same as turning the thing twice around the whole time, giving you the identity once again. And obviously the identity is also algebra preserving, structure preserving, because if we leave everything how it is, then it just stays how it is. And you can easily show that both of those are also automorphisms. The identity, trivially, is a bijection, because what do you need to apply to get yourself to the identity if you use it on the identity? Well, it's the identity in and of itself, so that's why it's the identity. It's its own inverse. And also it's an automorphism, trivially, because if we take the identity of A with B, this is the same as A with B, and this is the same as the identity of A in combination with the identity of B. So we have just proven very quickly that the identity is also an automorphism. What about the inverse of sigma? Is that also an automorphism? Yes, it is, and this is very easy to prove. Obviously, sigma to -1, the inverse is invertible because you are going to get sigma out. It's the inverse relationship that we have defined here. And now what we could basically do to show that this right here is also a homomorphism is just start with the original statement, basically. So we are going to start with sigma of A in combination with B. We need to show that this is equal to sigma of A in combination with sigma of B. Now this right here holds, it's an homomorphism. But we need to show that this is also true for the inverse. And here is where a bit of your calculus knowledge might come in. Because if we say that sigma to the -1 of x is equal to A, and we say that sigma of the -1 of y is equal to B, then if we apply the original function on both sides, we are going to get out that this right here is equivalent to saying that x is equal to sigma of A, and y is equal to sigma of B. I hope you can follow along. This is just the regular stuff that you do in calculus if you have an invertible function. And now we can use this logic over here. Now, if you take a closer look, we have that sigma of A is equal to x and sigma of B is equal to y. Now, what is going to happen if we now apply the inverse function on both sides? Now if we take inverse sigma on sigma, this is going to turn into the identity by definition, meaning if we use the inverse function here, we are going to end up with A in composition with B. Now, using the inverse function over here, we are going to take the inverse function of x in composition with y. But what are A and B? A and B are overall just the inverse of x and the inverse of y. So this right here is going to be equal to, if we take this side and apply this logic over here, this is the inverse of x in combination with the inverse of y. And would you look at that? Look at this little fella. It's a homomorphism and it's bijective. It's also an automorphism. Now what does this tell us exactly? So we have shown that three things are in automorphism on our original set G. They are all structure preserving. Doesn't matter what we do to the symmetries, they basically preserve everything that we have done originally. And they are all part of the so-called automorphism group. This is just a set that has all the automorphisms in it. We are going to denote it by the automorphism, aught, of, and we have G in combination with our binary operation circ that we have here. This right here is the set of all the automorphisms that we find in our structure, which is the identity for now, sigma, and sigma squared, which is the inverse of sigma. Now, are there any other structure-preserving operations in here? What could you do with such an equilateral triangle other than rotating it? Well, you could basically flip corners around and see if the structure is going to be preserved. This is just rotating it through a different dimension. Now, what would happen if we switch the corners? P with S. Our structure isn't preserved, obviously, because scissors doesn't beat rock. It's the other way around. So this right here, just by this logic, by this switching around the corners, this swapping, this right here is an automorphism because it just doesn't preserve our original arrow notation that we have introduced here in our directed graph. So switching those isn't an option. It's not an automorphism, but it's a part of the symmetric group for our sigma. Basically, there is the so-called symmetric group of order. This would be the S6, I think, because we have 6 things we could do. We can rotate it, rotation being denoted by this, or we can swap all the corners. The swapping is going to be denoted by, for example, swapping R with P, or swapping S with P, or swapping R with S. But those are not part of the automorphism group because this just doesn't hold. It's just not structure preserving, as mentioned previously multiple times. So those are the only 3 structures that we can find which for our directed graph are gonna result in automorphisms. Now, how is this helpful and how does this trace back to the original point of the video with the cyclic nature? Well, I already mentioned it. This thing right here is cyclic. Doesn't matter which of those you are going to use. If you use it enough, you are going to get back to the original position. In abstract algebra terms, this just means that there is a single element in here which can generate all of the elements inside of the set. And this element is obviously our sigma. So in abstract algebra, we say that a structure is cyclic if there does exist an element, and this element is going to be sigma, such that if we apply it multiple times, we are going to get the entire set out. This right here is the notation for the generator of a cyclic group, And obviously, sigma squared is going to be just sigma, but applied to itself. And the identity is just sigma cubed, meaning we can take our generator, apply it multiple times, and get everything out here in the set. And this thing has to order 3 because you have to apply it 3 times to generate all of the elements in here. This is why the automorphism group of G under this operation is a cyclic group of order 3, with this being the generator. Meaning overall, we have taken rock, paper and scissors and turned it into a fantastic algebra problem, which actually covers a bunch of things, a lot of things that you can find in here. And there are way more things that we can actually wiggle out of rock, papers and scissors, like the Silo theorems, which talk about orbits and also fixed points, just generally talking about actions on groups. And this is what we are probably going to cover next once I have the script ready. So I hope you did enjoy what you have seen today. I certainly had a lot of fun, and brushing up on abstract algebra right now is seriously fulfilling. I'm having a lot of fun, and I did not expect that this simple game could end me up with so much content for you guys. So let me know down there in the comments below if you found it interesting what I talked about here today. And let me know if there are other things that you would be interested in. Doesn't matter if it's abstract algebra or anything else. I think it's a cool topic, and I think I can put more stuff out that has to do with abstract algebra, and it actually performs pretty well right now. I didn't think that it would. So yeah, I thank you guys for watching. If you did enjoy this video, please like and subscribe and recommend the channel if you like. That's what I said back in the days. And also you can become a Patreon supporter if you wish. And I'm at the next video. I wish you guys a fabulous day. See ya.